one day in Ho Chi Minh because
Okay,
I'm going to.
So you want to meet our lab student, your class
Yes.
student? Okay.
Yes,
So,
if they want for me to explain more exercises and to do more exercises also in MATLAB, it will be great.
yeah.
So on Monday 11, if whenever you wish, I can be there to.
Okay, I understand. But okay, I invite you visit my lab, and our lab student will together. Okay, and try to talk something. Ignore your class, don't worry. Okay, I would like to make the concrete bridge for next our what we say our research together. There is a lot of things interesting I'm doing now, and if you interested, we can go together with the student. Okay. So we fit that in the next month in 11th. That means morning. Okay. I invite you visit my lab. Also in our university. Okay. And the student will gathering together. Okay.
Okay. Great.
Okay. So now you can go ahead. Okay.
Okay. So should we wait for the students? Because I see that there are only 7, so I'm going to wait for all the others while I'm sharing my screen, okay? So I'm going to wait a bit for all people to join, and I'm going to start, okay? Just tell me if you see my screen. Can you see my screen? And you can hear me well. Right? Yeah, so I see that 10 people join. I'm going to wait just 5 minutes so everyone can join. Okay. Just confirm me that you can also hear me well, so that I'm not, talking alone. Can you confirm me that you hear me okay? And should we wait also for the other students? I see that there are only 10. Do you think that? Okay. Great, great. I'm going to wait a bit for the others to join. I see that there are only 11 students. So I hope that you remember what we did last time. So last time we have discussed a bit what type of, the discussion was dedicated mostly to the analysis of the system. So once we want to control and to synthesize a controller for a certain system, we need to take into account certain constraints, if you remember. So first of all, for us, it's very important to, to reject perturbations, to account for perturbations which may affect the system. And we have different types of perturbations. Perturbation for the controller, yes, perturbations which affect the system, or perturbations which affect the measurements. And these perturbations which usually affect the system are appearing at low frequencies, and the perturbations may affect the sensors, usually appear at high frequencies. And so the idea was to first take into account disturbances when synthesizing our controller, and once the disturbances are rejected, it means that we can also follow, let's say, the reference, and to reduce, in case we have an overshoot, to reduce this overshoot, we may add we call it here a pre-filter here. So this was done last week, and the 5 constraints which we always need to accomplish while synthesizing a controller are the following. First of all, we need to ensure that we have internal stability. What do I mean by interstability? It means that all the transfer function between all the inputs, let's say, which enters into the system. So it means that between the signals, the reference, the input perturbation, output perturbation, measurement perturbations, all these transfer functions here need to be stable. Yes, it means that they need to have the poles within the unity circle. Yes. Next constraint was to handle stability. To handle, so once we have stability, we need to check how far we are from the stability margins. Yeah. So this is also a very important point. We need to ensure that we have sufficient stability margins. And you have seen that we analyze this through the gain margin, the phase margin, and also the module margin. The module margin is mostly dedicated to the robustness analysis of our system. Okay, so the third constraint was to ensure a small tracking error, yes? So here, I would like to have this epsilon here, yeah, to converge to 0, right? The difference between the measurement and the reference should be 0, should converge to 0. And we have seen, and we have demonstrated this, we have seen that actually, in order to ensure this, we need to impose, if you remember, an integrator into the synthesis of our system. we saw that we need an integrator, because if I write, for example, this transfer function, this controller here as a fraction of two polynomials, we have seen that we need this polynomial here, s of z, to contain a pole in z equal 1, if you remember, right? Why? Because like this, we ensure that we reject disturbances, and this means that the tracking error goes to 0, yes? So this is the main reason of an integrator, to reject perturbations. Okay, so this was the third constraint, and we have demonstrated how we can take it into account. The fourth constraint was to limit the sensitivity of the system faced to measurement disturbances, right? Because the sensors which may affect our system, the sensor which the sensors which actually read the output of our system may be affected by disturbances. For example, temperature, I don't know, different type of disturbances which may affect the sensor. So this is why we need to limit the influence of the perturbations for the sensor. So we have seen that to do this, we place ourselves in high frequency, of course, and in high frequency, we have seen that the sensitivity function appears within the appears in the link between the input of our system and the measurement error. The sensitivity function appears here. So the idea was to use the approximation that at high frequency the sensitivity function is almost 1. So this is why we have seen that we can impose a condition over the gain of our controller in high frequency. So the gain of our controller in high frequency should not trespass a certain limit. Yes, this limit which is linked with the limit over the actuator limits, of course, and the amplitude of the perturbations. So this is how we limit the sensitivity of the controller to the measurement perturbations. So we should not have a high gain in high frequencies for the controller. Okay, and so these 4 constraints here are necessary for designing our controller. Once we take this all 4 into account, at the end we see if the reference is well followed, in the sense that in case we have an overshoot, then we may add, which is not allowed of course, then we may add a pre-filter. Yes. So if you remember, we have looked. So here we add a pre-filter with the price that the response time may become slower, right? But we may diminish the overshoot which appears into the system response. Okay, so this is the advantage here. Okay, nice. So this is what we did last time. I hope more colleagues joined. Great. All the notes that I put last time, please check all the time the folder that I'm sharing with you, because these notes are going to be there. And how we finished the lecture, actually we did some exercises, if you remember. We did some exercises where we have to choose, for example, the sampling time, such that we maintain the stability of this feedback system. Another exercise was this one here. Another exercise was this one here, where first of all we we need, if you remember, for digital systems, for systems which we discretize, yes, in closed loop, we need to be sure that we respect the Shannon theorem, yes, when we discretize the systems, yeah, and we avoid the replayement du spectrum, yes, of the spectrum. So we have to add a filter, yes, which actually filters, the output of the sensors, the measurement output, which may be affected by, of course, also disturbances. So it is reasonable to add a filter here, but in the same time, we need to be careful that adding a filter within the closed loop may bring us some inconvenience. And we saw that some of the inconvenience are the fact that, first of all, we reduce the stability of the system. If you remember, we computed the gain K here such that this system is stable with or without the filter within the system. This filter which actually acts as a delay in the closed loop system. And then we also wanted to evaluate the phase margin of the system. And indeed, also for the phase, if we add delay into our system, yeah, the phase as well, it is reduced. Yeah, so reducing the phase, it means that of course we reduce the stability of the system. Yeah. I would like to ask you if you finished this exercise. Did you try to finish the exercise? And if you finished, can someone tell me the result? Did you finish this exercise, which we started last time? Did you finish it? Yes, maybe not. Okay, so if you remember, in order to compute the phase margin, of course that we use the definition, right? The phase margin, it's how far we are from P, yes, with the phase of our system, yeah? So the definition is here. Is P plus argument of the transfer function, yes. Be careful that here is exponential g omega because we are in discrete time, right? And this is when the HBO, the system, it is at 0 decibel, right? Okay. So we analyze this we started, for example, with the system without the filter, yeah, KHZ. And if I remember well, we analyzed, first of all, when HB of exponential g omega is 1. And the only thing that it remained, so we find out omega 0, yes, when we are placed at 0 decibel, and then 0 dB here. So then we have P plus argument of g omega. So here, maybe just to remind you that here we are at the open loop. And the only thing that it remains is to calculate this argument here. Yes. Just I can I can note this one with h prime of g omega. Yes, in omega 0, of course, because now we find it out. So what we have here, so first of all, h prime of g omega 0, right? Or we can call it exponential, yes, because we are in discrete time. So it's b. It was one of my notations, right? 1 minus alpha exponential minus g omega, which is, so I'm going to multiply here with 1 minus alpha. So exponential b omega, 1 minus alpha exponential minus g omega, over 1 minus alpha so what I'm going to have b, so this exponential minus g omega, I'm going to write it in using Euler cos omega plus g sin, or in this case it's minus. So 1 minus alpha. So this one is cos omega minus g sin omega, but with this minus here, I'm going to have plus cos omega plus g alpha sin omega over. So what is my intention is to compute the argument, right? Okay. So here I'm going to multiply these two, 1 minus alpha exponential minus g omega minus alpha exponential minus g omega plus, when I multiply them both, I'm going to have alpha squared. So we go further. This is a notation. H prime is not a derivative. Yes, please consider this. Just a notation I did. So here I'm going to have b 1 minus alpha cos plus g alpha sin. So here it is cosinus, right? One minus 2 alpha cos sorry, here I wanted to say, just because okay, so now it's more clear, I hope. So here I did not want it to put the minus, right? I multiply with the plus. So now it's more clear, I hope. So this is why 2 alpha cos omega here. Okay. It's too early for me. It's 6 o'clock in the morning. So, okay. So please be careful if I do any mistakes here. You should correct me. Okay. So plus alpha squared, right? Yes, here I use the fact that cos the omega equals exponential g omega, right? Plus over 2. So this is why I put these 2 here. Yeah, it's from this. Okay, so now I'm ready to compute, right, the argument of this. This is equivalent with saying that the argument of h exponential g omega, it is equal with a tangent So alpha imaginary part over the real part, yes. Okay, great. And now I computed this. And what is remaining, because this is my, so I obtained this. So my phase margin P A tan alpha C over 1 minus alpha cos. Okay? Just to, then if I want to compute for the case where I add the delay into our closed loop system, the only thing that it changes, yes, the only thing that is changing is this here. Yes, the fact that is this argument here, right? And if you remember here, yes, here we had also this part, sorry. So we had this part here, because this I noted with this. So just do, so we had P plus this argument, but this argument here, it was here. So P minus omega 0 minus this argument. Okay, so the only thing actually that changes, it's here, yes, is this argument here in the computation. If I add a delay here, we are going to have something like this, right? I meant here. So if we add a delay, we have that. The fact that we need to compute this here with the notations I did. Just me remember what notations I did. So it means that we have to add a z minus 1 here, yes. Here, a z minus 1. So z minus 1 usually is written like this, right? Exponential minus g omega 0. So it means that we have that in the argument of hbo of exponential g omega 0, we add a z minus 1, which is this, right? So with the notations, hbo of exponential g omega 0, I'm going to have argument of b exponential minus g omega 0 multiplied by minus G omega 0, right? And then the rest remains the same. So this argument, it is argument of exponential minus G omega 0 plus argument of exponential minus G omega 0 plus argument of B over 1 minus alpha with the notations I did this. So this one we already computed. Right? So I'm going to have minus omega 0 plus this argument here, which we already computed. So when we add the delay, it means that, so with the filter, the anti-replacement filter, our phase margin, what is going to be? So it will be P minus 2 omega 0. So I am decreasing the phase margin plus here it should be minus, right? Here it should be minus, yeah, because it's the denominator. Oh no, it's fine. Sorry. Plus. Just to see what happens here. So if this, okay, so here it's also plus, right? Plus this. I think so. Because it's argument of this, argument of A multiplied by B, it's argument of A plus argument of B, right? So I hope that I did not do any mistakes here. This remains like this. Okay, in any case, I'm going to give you this and you can check if I added or so here I'm going to have A tangent because it's this, which I already computed. So if I add n delays, in the closed loop system, it means that here, for the phase margin, I'm going to withdraw, right, n omega 0. So the conclusion is that when we add delay in the system, but just I remind you that this delay actually appears because we have included a pre-filter, which, does its job in the sense that we can filter the the output of our system, yes, to account for replayment of the spectrum, yes, because we pass from continuous to discrete. So it does its job, but in the same time, it brings an inconvenience. So we need all the time to be careful what type of pre-filter to add, what its order, and so on, so that we don't lose too much. Yeah, we may decrease, for example, the stability, but not too much either. So when we add delay in the system, we lose in performance in the sense that stability or phase margin. So I guess we have responded to exercise 4, where we evaluate the phase margin. And then we have 5 and 6. For 5, do you have any questions until now? Do you have any questions? So I guess there are no questions. So for exercise 5, we have to represent or to show that the response time, yes, in discrete time, when at the input we have a reference, yeah, which is echelon unitaire, which is a step, right? So we need to represent the response time. Yeah. I remind you that this is the exercise, right? So it says that at the input, the consigne, the reference, YC here, it is a step function. So we have to find out the response, Y. Yes. So what does it mean? It means that this is my closed loop system, right? Here is the, so 5. So here it's the controller, K, the gain. We had our HZ, yeah, with or without the filter. So maybe we can take it without now. Then with the filter, with the filter would be the same. This is the output, and so the question is to find out the response of our system, yeah? So it means that I need to consider Y over YC with YC a step. So the question is to find out Y, the response time, YK, right? This is the question. With YC a step, so I am putting as the reference the step, find out the time response of the system. Yeah, so what we are going to consider. So the transfer function between the output, the response, and the reference here. In my case, I noted with YC. So what is the transfer function? Well, of course, that is the closed loop system. Again, it will be the same if you add the pre-filter here, if you add the Z-1 here, right? It will be the same, just that you need to take it into account here. Okay. So how you find out the response time? Of course, in time domain, because here we are in frequency domain, right? Here we are in frequency domain. So how we are going to solve this? How I'm going to find out YK? Sorry, my microphone. So do you have any indications for me how I'm going to find the response time in discrete time? Well, we just have to replace here. We use the properties of the Z function, yes, of the inverse, and we find out YK, right? Let me see how we note it HZ. HZ is this one, right? This is our notation, 2, 1 minus alpha, Z minus alpha. So YZ over YC of Z equals K 2, 1 minus alpha over Z minus alpha over 1 plus K 2, 1 minus alpha over Z minus alpha equals with, so I'm going to have here 2K 1 minus alpha over Z minus alpha plus 2K 1 minus alpha. Okay, so what I should, this K is the gain, right? This gain here. Yes, it's not the time. Yes, the discrete time. Here, the discrete time, I note it with smaller K. So I'm going to divide by Z so that the Z minus 1 operator appears. So I'm going to have 2K 1 minus alpha Z minus 1 over 1, let's say, minus alpha Z minus 1 plus 2K 1 minus alpha Z minus 1, right? So now I'm going to multiply what I have, YZ, it is YC over Z equals 2K 1 minus alpha Z minus 1 over 1 minus alpha Z minus 1 plus 2K 1 minus alpha Z minus 1. So I'm going to multiply in across so that I can find Y. So I'm going to have YZ minus alpha Z minus 1 YZ plus K 1 minus alpha Z minus 1 YZ equals 2K 1 minus alpha Z minus 1. And this is the step, the response, the reference, yeah? So YZ here equals, I'm going to pass everything on the other side, alpha minus 1 YZ minus 2K 1 minus alpha Z minus 1 YZ plus 2K 1 minus alpha Z minus 1 YCZ. Okay? So now I'm going to pass in time domain, right? Here I'm in frequency domain, right? Using the Z transfer properties, YK. So my response time, it is alpha YK minus 1, because here I have Z minus 1 multiplied by YZ, minus 2K 1 minus alpha YK minus 1 plus 2K 1 minus alpha YC K minus 1. So the response of my system depends on the previous response of the system and the reference input. But I remind you that YC of K is the step, right? The step. This is the hypothesis. This is what we had in the exercise. So this means that YC of K, it is 0 for K smaller than 1 and 1 for K bigger and equal than 1. Okay? So if I want to see the representation of the response in time, I'm going to start to give some values, in time for the response. For example, for Y0, I'm going to have alpha Y minus 1 plus 2K. This value of the K is given in the exercise, in the previous, for this K 1.5. This one is something that you can replace after. Y minus 1 plus 2K 1 minus alpha YC minus 1. Yes? So here, I'm going to consider that all the initial values are 0. So I'm going to consider that this is 0. If I did not give them the values, the initial condition, then mean I'm going to take them 0. But if I give the initial condition, I could have given at the very beginning of the exercise that Y minus 1, it is a certain value. But if I did not give them, I take them 0. Okay, by default. And this one for K equal smaller than 1, it's 0, right? So Y0, it's 0. Then for K1, I'm going to have Y1 equals alpha Y0 minus 2K 1 minus alpha Y0 plus 2K 1 minus alpha. Here I'm going to have 0. So this one, it's 1 now, right? Because I'm in the case when, sorry, I don't know why I wrote this, right? This is the step. Why you don't pay attention to me? So no one corrected me. It's the step, of course. So for the step, for K equals 0, it's 0. For K smaller K, it's 1, yes. So here we have 1. And the rest is 0 because we found out that this is 0. So Y of 1, it is 2K 1 minus alpha. with these values k and alpha given. These are the notations given before. So then you can continue, so you can find out, your answer. Of course, in MATLAB, if you introduce this, you can say this recurrence relation, you can obtain your answer. So here, for example, y2, what I'm going to have? I'm going to have alpha y of 1 minus 2k 1 minus alpha y of 1 plus 2k 1 minus alpha yc of 1, right? So here, this is 1, and then this y1 here, you need to replace it with what we have here, and then you are going to obtain the other step of your response, until, of course, you will obtain the response yk over time, something like this, right? It will be up to you to continue with the computation, right? Of course, and then you can represent it using a certain sampling period, TE. And then if I look to the last question, 6, the last question asks us to represent also the response of the system when a command or an input perturbation also is added, and this input perturbation is a step. So the question is, now, the question is like this. Find out this PU, find out this is plus, find out the output, the response YC when we apply an input perturbation PU, which is a step. So it means that it asks me the direct link between the output of my system and the perturbation here. So if you go back at the very beginning of my course here, last time, I computed for you all the transfer functions between all the input and the outputs. So what is the transfer function between Y, the output, and the perturbation here, this perturbation, the input perturbation? So what is the link between Y and the input perturbation? You can see it here, PU. The link between Y and PU, it is H over 1 plus HC, right? So why this is important? When we want to analyze how the system behaves when we apply a perturbation, of course that I'm going to analyze the transfer function between the output and the perturbation, yes? So Y of Z over PU of Z, it is, in my case, we said H of Z over 1 plus K H of Z, yeah? And the question is to find out YK, to see how the response behaves based of an input perturbation, which is step in our case, right? So you are going to do exactly the same thing what I did here. Yes, you have to write your transfer function, you replace here, and then you need to find out, yeah, using the Z transfer, you need to find out YK. Just that is for a different, so you just need to replace here. I'm just going to start this. Here, AZ, it was 2, 1 minus alpha over 1 plus alpha Z. I think it was this, right? Let me remember. No, it was 2, 1 minus alpha, Z minus alpha. And then 1 plus 2k 1 minus alpha, Z minus alpha. So this is equal with 2, 1 minus alpha over Z minus alpha plus 2k 1 minus alpha. You check here. You can divide by Z by Z. Like this, you'll have the Z minus operator 1 minus alpha Z minus 1 doesn't plus 2k doesn't change too much with respect to the previous exercise. Okay, and then you start to multiply in cross here, so you'll have YZ minus alpha Z minus 1 YZ plus 2k 1 minus alpha Z minus 1 YZ equals with, this time it's the perturbation here. So from here, you need to find out YK. So YK equals by using the Z transform properties. Do you have any questions? Did you understand what I did here? I guess it's very hard online to ask questions. So no questions. You know, when you have no questions, it means either that you understood everything, either that you did not understand anything. And this is, the second case would be very, very sad. Okay, so we take a break. You can see each other at, for me, it's 7 in the morning, so, okay. Okay, so now we can continue. So I guess the RLC circuit we already did it. So I just finished this exercise. Again, if you have questions, you can also ask me by mail. You can always ask it. It seems that you don't ask too many questions, so it will be. So if you want to ask more questions, please don't hesitate to ask. I hope to also see you in person, and like this you can ask more questions. So this exercise, RLC, we already did this exercise. These are very simple exercises. I can let them for you. One exercise that I would like to do with you before starting with the controller synthesis is this one, exercise 15, where I'm asking you to find out the sampling time, yes, for this system, such that in closed loop, this system, it is controlled by a controller, corrector here, controller regulator, which has the limit that in high frequency is the gain of the controller in high frequency is less than 10. So this is the only hypothesis that we have. So the question is, find out the sampling time for this system, which in closed loop, it is regulated by an input, by a controller, which has the limitation that in high frequency, its gain is less than 10. Did you understand the question? So, exercise 15. So we have this system. It's a second order system, right? Anyway, I take it like this. It's okay. So the question is, find out the sampling period T for this system, which is controlled by a controller for which its gain is less its gain is less or equal with 10 in high frequency. So it means that this system is controlled by, so minus plus, by a gain, by gain K, for which by an input K, for which its gain is less or equal than 10 in high frequency. So this is my HP. So the idea is to find out with what sampling time we can discretize this system. So it means that we are in high frequency, right? And if you remember, last time I did with you I showed you when we will synthesize a controller, we will have to obtain transfer function in open loop, which looks like this. This is the ideal form. So if we want to have all those constraints accomplished, it will be great to obtain a transfer function in open loop like this one, HBO. Right? This is the ideal shape of the system in open loop, such that we respect all those constraints. And we have a relation between the open loop and the closed loop. If you remember T here, it is actually the closed loop. So if we obtain this ideal, let's say ideal shapes for the closed loop, for the open loop, and for the sensitivity function, this means that all the constraints with which I started this course are fulfilled. Okay, so if so, you remember that in my exercise, it says that we are in high frequency. So if I go back and I remind myself, what is so the exercise says that we are in high frequencies here. So again, I remind you, this is a reminder. So the ideal shape of the closed loop, the open loop, looks like this, right? This is the open loop, HBO of G omega, right? So here in low frequencies, HBO is bigger than 1, and in high frequencies, HBO is smaller than 1, right? Then this is the ideal shape of the sensitivity function, yes? This one, which is 1 over 1 plus AC, if you remember, right? This is the ideal shape, right? If you remember here, we have 1 over module margin. Okay? So this in low frequencies, this S is 1 over HBO. And in high frequencies, this S is approximated with 1, right? And then the closed loop, TG omega, which was AC over 1 plus AC. This is its ideal shape that we would like to arrive. So here in the low frequencies T, it was approximated with 1, and then in high frequencies T was approximated with HBO. Exactly with the open loop. So this is where I wanted to arrive actually, because this tells us that in this exercise, the hypothesis, the hypothesis tells us that we are in high frequency and that the gain of our controller is limited to 10. So it means that if we are in high frequency, since we are at high frequencies, T, which for us is the boucle fermée closed loop, it is approximated with HBO in high frequencies. And the gain of our controller is limited to 10. So in high frequency, K is smaller or equal than 10. I wrote a nice K here. Sometimes I don't write very nicely. Okay? So what I'm going to do? Well, I am going to compute HBO. Yes, I'm going to go in frequency domain, right? So HBO of G omega, it is 2000 K. Let's take it a smaller number here. The same thing, right? 2300 K. Oh. 2300 K over P squared plus 70P plus 60. Sorry, I wanted to replace with G omega, right? Okay, so I'm going to have P squared minus omega squared plus 70 G omega plus 60. Okay? So I'm going to place myself at 0 decibel, if you remember. Yeah. So here in discrete, yes, in discrete time, in frequency domain, usually we stop here at omega max, right? So this is my, let's say, transfer function, for example, in closed loop or open loop. And we stop here at omega max. Omega max is P over TE, right? This we showed, right? So I'm going to place myself at, for example, at 0 decibel with this. And of course that the pulsation at 0 decibel, it is smaller than omega max, right? The pulsation, the maximum pulsation. So module of HBO of G omega, 0 I call it, it is 1 or 0 decibel dB. Okay? So I'm going to calculate omega 0 at 0 decibel. And this omega 0 at 0 decibel, of course, that it's smaller, should be smaller than or even equal than omega max, right? This is a condition that we need to improve. So here we are going to find out the sampling time. Yes? So just to module of HBO of G omega 0, it is since we are in high frequency, this one, of course, is smaller than this one in high frequency, right? We are in high frequency. So here I'm going to have module of 2300 K over square, right? If I put it square, this should be plus, right? Or I'm going to see after
just to write you from the beginning. So it's omega 0 plus 70 j omega plus 60. This is the module. Okay. In high frequency, this one is smaller than this one, much smaller in high frequency. So this module, it is actually 2300 K over omega 0 square, right? Equal 1. Okay, so from here I have that omega 0 square, it is 2300 K, yes. K in high frequency K was smaller or equal than 10, because this is what the hypothesis tells us, right? With 10 in high frequency. So I'm going to see that omega 0 square, it is, maybe I write directly, omega 0, it is a square tail of this, 10. And then I am going to impose the condition that omega 0 is smaller or even equal than omega max, the maximum, which is P over TE. So I'm going to have that 2300 multiplied by 10, smaller or equal than P over TE. So my sampling time, TE, is between, of course, bigger than 0 and smaller than P over this value. So I'm going to let you compute this value here. So we found out the answer. So I suppose you don't have any questions. Do you have any questions? So before starting to do also some exercises for the implementation of a PI or PID controller, I'm going to introduce you a bit the rest of the course, right? Because until now we just did the analysis where we want to maintain some constraints when synthesizing a controller. Now I'm going to show you how to choose those parameters of the classical PID. But this is in discrete time, yeah. So this part already is done. So before going into this, I remind you that we said that in order to reject perturbations, we need to add an integrator in our system. Okay, this is great, but we need to be careful, because adding an integrator in our system, and if the tracking error, yes, here is affected by disturbances, it means that we integrate those disturbances and we may actually obtain very low performances, in the sense that the response, for example, it might have overshoot, it might be oscillating. So this is why just to give a bit of insight. So we have we have our controller, right? Here, C of Z. And then we have our system. Here is the output. So we find out the controller, but we need to be careful that the actuators of the system, they have some limitations, right? As when we find out our controller, the PID, whatever you want, we don't take into account the limits of the actuator. So what we do, we have to add a saturation here. We have to add a saturation, which takes into account the limits. So here it's U, and here by adding this saturation, I will have U max and U min, right? So I need to U saturated. I'm going to send to the system I need to send to the system the values which are, are realistic for the actuators, right? Maybe for a DC motor, I cannot send the inputs more than 10 volt, right? So this is why we add here. So, but we need to be careful that by adding an integrator in our controller, the fact that we add this saturation here might cause problems, because in the sense that we don't want to stay too much either on U max, either on U min, of course, right? Think about sending to an actuator, to a DC motor, sending for many steps U max, right? Or U min. So an input which stays in the limits. Well, we might destroy that DC motor, so it's not at all good. So this is why we should add not only limitations for the controller, yes, just to remind you here that I'm talking about the integrator part. So we should not add limits only on the U max and U min, but also we should add limit on the variation of the controller, right? So this is what I'm saying here. So we have to send to the actuator values which are reasonable, which are realistic, which respect its limits. So this is why we add the saturation. But also we need to forbid to stay too much in saturation, because if we stay too much in saturation and then we integrate that error, tracking error here, then it means that we may add some oscillation into our system. So we need all the time to not add only also the input UK between U min and U max, but also delta UK should stay between U min, delta U min maybe, and delta U max. Delta UK, what does it mean? It means that the difference between the controller at the current step and the previous step, right? Okay? So this is an example here. You see, if we don't have, we call it anti-wind up, yes? And I'm going, maybe if I have time, I can, today I can go into detail more, but let's see. So just an example here. So if we don't add, for example, these limitations for the variation of the controller limitations. So here in green we have so here in red is the reference that we want to follow.
Yes, in red is the reference that we want to follow. In green is the response of the system without taking into account those limitations, also the variation of the inputs. And here it's actually our input. Here it's our input in green without taking into account the limitation, the variation, and in blue with taking into account. So with anti-wind up, we call it. So you can see that without taking into account the limitation of the variation, you see that the response in green is more oscillating. I even have some overshoot here, right? And in the controller, you can see the controller limits is between -1 and 1. And the controller, you see that I stay too long time. You see from 15 here to 35, yes, 20 minutes I stay into saturation at the maximum limit. And then again, also here, I stay too long time in saturation at the limits, yes. This is why by adding methods for anti-wind up, by limiting also the variation of the controller, you can see that the response in blue, of course, it has the same time response, but the response is, so I diminuted doesn't have, of course, the same time response, but what I wanted to say is that I diminuted the overshoot, yes, and the oscillation in the response. And in the same time, the controller, the input, as you can see, stayed less in the saturation, yes, you see, and it becomes smoother, right? Has less variations, which is great, yes, because I don't want to send to the controller something which, to the system, something which varies too much or stays too much into the limits, yeah. So this was anti-wind up. Now I'm going to pass a bit how to choose the controller. So I'm going to directly pass to different methods. So for synthesizing our controller. What is important is that when synthesizing our controller, we need to respect those constraints that I showed you in my previous course. So I'm going to pass directly to these methods. One method is to determine the controller by using pole compensations, in the sense that we may compensate for the dominant poles, yes, and I'm going to show you immediately what does it mean. We may have a method where we model the open loop to obtain that ideal form that I showed you in my previous course. So we call it loop shaping, or we can place the poles directly in the closed loop. We call it RST structure or pole placement. Yeah. So these three methods are really, really important, and I'm going directly to pass at this. Just to remind you that we are in discrete time. This is our classical PID structure, yes. And what it is important is to, so here we have the PID structure, for example, in parallel, yes. Here we have the proportional, here we have the integrative, here we have the derivative part. So when I want to obtain the discrete PID, I can use one of the methods that I proposed you in my lectures in the very beginning, right? So I can use Euler implicit, for example. It means that I replace P here by 1 minus Z minus 1 over TE. So by replacing this, I obtain this form, this discrete form of my controller. With Ki and Kd, of course, being a relation between T, the sampling time, and the
parameter of the integrator in continuous assignment. Here, the same thing for KD. Yes. So it's up to us what discretization method we want to choose. Either we directly synthesize our controller in discrete time. Yes. Of course, by first discretizing the dynamical model of the system. Either we can obtain the PID in continuous time, and then we can discretize it if we want to implement it on a microcontroller, for example. And what I also want to remind you, in one of my courses, I said that when we implement transfer function on a real system, on a microcontroller, we need to pass through the factorization. We need to write it in the factorized form so that we don't have any problems with changing the gain, the poles, or the zero of the transfer function. In the sense that we want to keep the property of the system. Okay, so I'm going directly to the methods. Yes. If you want, you can check the other slides, but what I wanted is to show you directly the methods for synthesizing your control. So, the first method is called method de compensation de pole dominant. It means that I'm going to compensate for the dominant poles. Yes? So, what we are going to do is to consider our controller like a fraction of the two transfer function of two polynomials. This is my model. Yes, fraction of two polynomials, b over a. This is known. And we may have also perturbations. And if you remember, the main goal of a controller is to reject perturbations. And after, to follow the reference, right? Because if I reject the perturbations, of course, then I'm going to follow that reference, yes? But first of all is to reject the perturbations. This method de compensation de pole dominant, it only works, yes, for system HZ, which are stable, yes? If the systems are stable, then I can apply this method because I can compensate only stable poles. I cannot compensate, I cannot discard, yes, poles which are not stable. Okay, so what is the first step? So this is what I say here with the first item, that it only works when HZ it is stable. So what I'm going to do, well, we look at the poles of our system AZ. We organize them nicely in the sense that I'm going to organize them from the most dominant to the less dominant. When I say dominant pole, it means that there are the poles which are closer to the limit of stability, right? We are in discrete time, closer to the unity circle. Those are the dominant poles, yes, because those are the ones that impose the time response of the system. If you remember, if we are closer to the unity circle, I'm going to have a slow response. If I'm closer to zero, for example, to the middle of the unity circle, the response is fast. Okay, so then I'm going to, the second step is to choose RZ here as the poles of RZ of this polynomial of the controller, because our role is to find R and S, right? This is our role, right? And once I organize this AZ in factorized form, I'm going to choose RZ as the poles dominant poles of AZ, right? What is important? It's important to note that I cannot choose C of Z, the order of C of Z, the order of this transfer function less than the order of the model. So we have an order of the transfer function here, at least equal with the order of the model. So this is why the number of poles which I am going to compensate, the numbers of poles of RZ from AZ, I'm going to choose them such that the order of the transfer function here, it's at least equal with the order of HZ. So once I find out that RZ are among the poles, has among the poles of AZ, then the third step is to choose SZ. So I already chosen R, which are the pole of A, and then for SZ, I'm going to choose it such that I respect the constraints which I showed you before. It means that I want static error to converge to 0. So SZ should have an integrator, yes, a pole which has Z equal 1, and then to ensure all the margins, everything that I showed you before. Let's understand through an exercise. So I'm going to give you this HP, yes? This is my function. This is my model here. And the question is, can you synthesize a PI controller for this model? Or a PID, whatever. So first of all, let's analyze this model, yes? So this model, is it stable or not? HP, is it stable or not? Okay, it's stable. Great. So HP is stable. So it means that if it's stable, then I can apply the method which I tell you. It means that I can apply the method for compensating the pole, la méthode de compensation des pôles dominants. Okay, I'm going to also have to pass in discrete time, right? Because I want to synthesize a digital controller in discrete time, a PI in discrete time. So another question is, what is the order of this transfer function? Well, this transfer function is of order 1. So I'm going to synthesize a controller which has at least order 1. Yeah. I discretized this with C2D in MATLAB. I did C2D just to So we take a very simple exercise. This is stable. When doing C2D, I obtain my HZ. Yeah, I obtain HZ. This HZ here, is it stable or not? When I pass to discrete time, did I obtain a stable system? Well, yes, because the poles here is in the unity circle, right? It's 0.9. And I did also, I wanted to see the behavior in frequency domain of HZ. As you can see here, I stop at omega max P over TE because I'm in discrete time, right? And we said that we analyze the response over 0P, then and so on, periodic P to up 2P and so on. Okay. So let's apply the pole compensation method. This HZ, it is written as fraction of two polynomials, B over A. We said B over A, right? And I'm going to choose R of Z here, R of Z, as the poles of AZ. But before this, let me remind you the constraints that I want to satisfy when I synthesize a controller. First of all, I want all the matrices, I want stability. Yes, this is very important. I want stability. Yes, all the matrices between all the inputs and the outputs of the system should be stable. Okay. Then I want to also be far from stability. Yes, if the model is known and I don't have any parameter variations, I'm going to take module margin bigger than 0.5, phase margin bigger than 45 degrees. If the system is unknown and I have, variations and so on in the model, I will be more preemptive, and I'm going to take a module margins bigger than 0.8, phase margin bigger than 60. Okay, so this is for the margin. Then I want static error null. Yes. What does it mean? I want the static error to go to 0. Yes. This means that, if you remember, we demonstrated that I need a pole in Z equal 1 for the controller. And then also, if you remember, to compensate or to account for measurement perturbation, I also need to limit the gain of the controller in high frequency. High frequency means that omega goes to omega max, right? In discrete time. Yes, we are in discrete time. So I need to limit this gain at N max, yeah, depending also on the limitations that I have on the inputs and the amplitude of the perturbations. Okay, so if then we have an overshoot, I may also add a pre-filter. So these are the constraints that I want to obtain. For example, I would like to choose module margin bigger than 0.8, phase margin bigger than 60. I will impose Z equal 1. If I have amplitude, the maximum amplitude of the Bruit, of the measurement perturbation, is 1, and so, over the input, and for the measurement perturbation is 0.1. And if you remember, also in my course, I said, in my previous course, I said that I'm going to find out the maximum gain of the controller in high frequency. I did some exercise. Let me see, here. So if you remember, I compute the relation between the input and the measurement perturbation. In high frequency, S equals 1, yes, or S equal, it's approximated with 1 over M. So here I have the gain of the controller, it's U over PB. So this is what I do here. The controller, and even since I have the module margin, you see, I take this U equals CSPB. Yes, so the gain of my controller should be less than equal than U over PB multiplied by 1 over S. So the gain of my controller, since for the input I have 1, for the measurement I have 0.1, so here I have 1 over 0.1 is given in the exercise, and 1 over S here actually is approximated. If you remember, I have a 1 over module margin, it is S. So this is approximated with module margin. Module margin for me, which I gave that I want to be 0.8. So this is equal with what I obtain here, 8, right? So I want, as a constraint, I also want that the gain of the controller should be less or equal than 8. In high frequency, right? We are in high frequency. This to limit the measurement errors, measurement perturbations, okay? And the controller that I'm going to choose a PI controller because I have an order 1 for my model. So I'm going to take a controller which has at least the order of the model. This is me who chooses. This is the PI. This is the proportional, and this is the integrative. And I remind you that we are in discrete time, and it's my choice to take it as this when I use Euler discretization. So let's see. C of Z, it is K1 plus Ki 1 minus Z minus 1. This is the PI controller, which I want to synthesize. And then for the model HZ equal with what I have here, 0.1903. So I remind you that the controller, I can write it R of Z over S of Z. So just let me show you. So here I have K 1 plus Ki K Z minus 1 plus Ki Z over Z minus 1. So K minus 1 plus Ki Z over Z minus 1. And then my HZ here, we also write it B of Z over A of Z. So I'm going to choose A of Z. A of Z, I know it, right? And I'm going to choose R of Z as the pole, most dominant pole of A of Z. So this is what I obtain here. Yes. So it's exactly what I wrote here. Just if you want, you can also divide by 1 plus Ki. Okay. So this numerator here from the controller, this is RZ. I'm going to choose it as the dominant pole of HZ, 0.9. Yeah. So just to write exactly like I have here. So it is K1 plus Ki, Z minus 1 over 1 plus Ki, Z minus 1. So I'm going to choose the pole of this This is RZ, right? The pole of this equals this. Yes? The pole of LZ is the pole of AZ. AZ, this one. So 1 over 1 plus Ki, it is 0.9 and what was written here. From here, I'm going to find out Ki. This is the value of Ki, which I found. So I found the value of Ki. It's around 0.1. Okay, nice. So this is done. Then I have to find out the value of K, right? So this is the parameter Ki of the integrative, but I also need to find out the value of K. How am I going to find out the value of K? Well, I'm going to find it out from the hypothesis, because in the hypothesis, I wrote that the gain of the controller in high frequency should be less or equal than 8. This is the hypothesis. So the gain of my controller, the gain of C of Z, in high frequency, when omega goes to omega max, I remind you that we are in discrete time, should be less or equal than 8. Well, I have to find out the gain here, so it means that I have to go with this here in frequency domain, and the omega goes to omega max, yes? What does it mean omega goes to omega max? It means that, if you remember, if I have Z equal exponential P TE, right? Or exponential P T, right? When I have P goes to G omega, right? I'm going to have Z goes to omega max, right? But Z for Z, I have omega goes to omega max, right? So this means that Z goes to exponential G omega max TE, right? But omega max, it is P over TE, right? So exponential GP here. So this is, what is exponential GP? This. So when I do omega goes to omega max, is equivalent with writing that Z goes to -1. Due to this explanation here, yeah? So I did this. The gain of the controller. So when Z goes to -1, so it's exactly what I wrote here. So K1 plus Ki over 2, yes, because this is my controller, the one here, written here. So K1 plus Ki over 2. So I obtained K here, because Ki, I already find it out, is 0, 1. So K, this is exactly my gain of the proportional. So I will impose that K should be less than or equal than 8. Great. So I found that the K is less than or equal than 8. And I also find out that the system, it is, that Ki, it is 0, 1. So once I found out these values, it's not finished. It's not finished that I found the parameters of my controller, of the PI, and that's it. No, I should go further and do all the analysis. Check the diagram of Bode for HBO, as you can see here in red. the diagram for the controller of both from the controller. This is C of Z. So I took, for example, I took for K smaller than 8, I took for K 2, the value 2, and then 0, 1 for Ki. And for this controller, for this AZ, we do all the diagram of Bode to see if the margins are fine. So the gain margin is 13.6 dB. If you go dB to magnitude, you'll see that the gain margin is bigger than 0.5. The phase margin, let me drink some water. The phase margin, it is bigger than 60 degrees. So here in this case, 78.5. I'm going to look also the module margin. So I'm going to do the diagram of Bode for the sensitivity function. So I'll have to do. So once I found out Ki, it is 0.5, and I found out that K0 is smaller than 8. So for a controller C of Z, in this case, I took it 2, 1 plus 0.1 over 1 minus Z minus 1. For AZ, then you need to do all the analysis. It means that I have to find out the stability. So it means that I have to do HBF, HC over 1 plus HC. So the system should be stable. Then I'll have to find out the stability margin. So I need to do the Bode diagram of HBO. I also would like to see the behavior of the controller, mostly to see if in high frequency the gain is smaller than 8. And you can also do the analysis. And then here margins will tell you, or even all margins will give you the margins, the stability margins, right? Because you like a gain margin bigger than 0.5, phase margin bigger than 60 degrees, and module margin will be great to be 0.8. Yes. For the module margin, what you do, you can draw the diagram for the sensitivity function. So both over 1 plus HE, or in MATLAB, for finding out the module margin, you can do norm, if you remember, because it's infinite norm of 1 over S at infinity. If you remember, the module margin is 1 over S at infinity. Yes? So this is what I did here. This is the module margin. So you can see that it's 1 over 0.08 here. So the module margin is exactly 0.8. And then the response time. So once I did this, I need to check the response time. To see if the static error is converging to 0, to see also the behavior at perturbations. You can introduce a step for this, and you need to do Y over PY, this transfer function, to analyze this transfer function. Yeah. You can also analyze the transfer function. So you need to analyze also Y over PB, the input, how the input behaves to the perturbations. Yeah. So here I did this. So this is the response time, around 1 second. And then here it is U over PU. So I see the response time for the a perturbation for an input perturbation, and you can see that I am stabilizing at 6 seconds. Yes, so I take into account the perturbations, but a bit. I took a step, right? Échelon step. So it's a bit slow when it comes to rejection of the perturbations. Yeah. So this was the method for the pole compensations. Just I remind you that it only works for stable systems. Yeah. The reason for which I apply this method is that it's simple, and I would like to reject perturbation, because even if the system is stable in a closed loop, it might be affected by disturbances. So I would like to reject perturbations. Okay. So let's take a break. If you have questions, don't hesitate to ask me. Let's take 10 minutes break, and then we will pass to the next method. In my case, we see each other 8:23. Don't hesitate to ask me questions if you have. I'm back. So, do you have any questions about this method? Do you have any questions? I hope we can do an exercise after I finish, and then I finish the lecture. We can do some exercises, and maybe you can understand better. So let's continue. Let's continue with the other method. So this is loop shaping. I hope I can finish both now. Loop shaping. So for loop shaping, what we want? Actually, we would like to arrive to this ideal form of the HBO, of the model of the open loop system. Why? Because if I have this open loop system, this nice shape, then it will be, I have a relation between the closed loop system and the open loop system, yes? So S, it's 1 over 1 plus AC, and T, it is HC 1 over HC, right? So due to this, I can also draw a conclusion over the closed loop system. Yeah. So I want to remind you that at low frequencies, we analyze the precision. Yes, the precision for the system, in the sense that we would like to diminish the static error, yes, and to account for output perturbations, perturbations within the system. But at high frequencies, we account for robustness with respect to measurement perturbations, which may appear within the system, right? And then here we impose, the time response for the system, and we need to analyze all the for everything. We need to analyze the stability margins, static error goes to 0, and then robustness with respect to perturbations, measurement perturbations. So just to give you a glimpse on how what is the ideal form of a PI, for example, PI controller. So here, the PI controller, it has this shape, and the reason for which we use an integrator is to eliminate the static error and to reject constant perturbations. Yeah, and to the gain here gives us also the time response. So this is the shape of the PI controller. But sometimes, if the PI is not enough, maybe, for example, we reject the perturbation, but we don't have enough phase margin or enough gain margin. What we do, we add in parallel with this controller here, with the PI, I add in parallel we call it lead lag transfer function. So together with this one, with the PI, I can add the transfer function like this. This is in continuous. Here is the discretized case. Yeah. But how I should add this? Well, I'm going to give you an example related to what we did before. So I'm going to add this CA of Z, this is in discrete time, such that I look here at the phase margin. If the phase margin is not enough, and if I want, for example, to add 30 degrees of phase margin, well, this omega 0 is the pulsation of 30 degrees, and then sin of phi, it is given by this value. So this is a relation between the phase margin, the phase that I want to add to the system, and the transfer function parameters. You see here, sin of phi, it's a minus 1, a plus 1. So here it's a relation between the phase of the system and the coefficients here, the parameters here. And the same I have for the pulsation. This is given, so this is some formulas that we can use, okay? And I'm going to give you an example. I take an example on how I use this transfer function in parallel, so in series, connected with a PI or even a PID, depending also on the degree of the system. For example, if I take this system HP, which is actually a system which contains an integrator, so it's at the limit of stability. It's not a stable system. So if I want to synthesize a controller for this one, in order to choose the method, I cannot use the one that I showed you before, the compensation of the poles, right? Why? Because this is at the limit of stability. The system is not stable. Okay, so I'm going to choose loop shaping this time. So I'm going to discretize this, analyze a bit the model. Yes, we are at the limit of stability because Z goes to 1. Here P equals 0. And let's say that I choose the controller that I synthesized before for the other system. So this is 2, 1 plus 0.1, 1 minus Z minus 1. So PI controller. With this PI controller, when I do the analysis, yes, I see that the gain margin, it's 45, dB, you can transform in magnitude. And I also see that the phase margin, it is around 18 degrees. So it's not enough. Me, I would like a phase margin which is at least bigger than 40 degrees, right? 45 degrees, even 60 if the system is unknown. So what we do, we can put in series with this controller here, that transfer function, this function, we add a lead lag PI or PI par avance de phase, we call it. I add this in series with this transfer function, the discrete one with that transfer function there, such that I can add more phase. So I can bring the phase at least 40 degrees. So when I do this, here is an analysis of the time response for that. So for this PI here, we did also an analysis for the time response, and you can see that it's very oscillating. And also for the module margin, it's also not sufficient. It's 0.3. So at least I would like it at least bigger than 0.5. Okay? So, like I said, we will add this type of transfer function in series with this one, such that I can add more phase. So the phase was 18. So I like to add at least 30 degrees to this phase to have it at least bigger than 45 degrees. So it means that in the formula I gave you here, if I want to add 30 degrees, I will do sin of 30 degrees, sin of 30. I will find out A, and then I'm going to see for which, it represents omega 0. Omega 0 here, it is at 0.3, yes, because the phase margin, it's 80 degrees at omega 0, 0.3, yes. So then I'm going to use the other formula where I can have T. And then this C of Z, this big transfer function. Here I'm going to put it in series. So series means that I will multiply it here. You see here, I multiply it with my PI controller, right? So it means that I increase the phase with at least 30 degrees by adding this transfer function. Of course, I increase the degree of the polynomial for the model, but with the advantage that I respect the constraints. So let's see. If I use that controller, then I'm going to have a gain margin 40 dB, a phase margin 48.5. So this was my goal, bigger than 45. This is great. I'm going to analyze as well the module margin. Well, the module margin, it is 0.8. I did here a body of sensitive function and I took the maximum, and here the module margin is 0.8, which is great. And then I'm going to also analyze the response, the time response of the system. As you can see here, this is the response time. I obtained tracking error static, which converges to 0. Of course, it's a slow response, 25 seconds. Of course, that this is due to also the model that we have. I remind you that we have a model which it's at the limit of stability, has a pole at the limit of stability. And here we have the response of a perturbation. So again, also the rejection of the perturbation is quite slow as well. If you want to also diminuate this overshoot, you can increase here the pre-filter here. I took it 1, yes. But if you want to decrease the overshoot, you can increase this by taking an order 1, for example, pre-filter. Yeah. So in order to implement this PI paravance de phase or lead lag PI, what you can do is to, of course, obtain the recurrence relations that I showed you, and then really implement it on a microcontroller, right? So these are, let's say, like some lines of code or coding for your controller, because you cannot implement the transfer function on a microcontroller, right? You need to first obtain the recurrence relations, yes, and then you have, this is the static error, which is the difference between the reference or consigne and the output. Then you have for each part of the transfer function. If you remember that we were developing in elementary cells, so first we had the factorization, and then we were developing in elementary cells, and we obtained actually the recurrence relations, which makes the relation between the output of my system, in this case it's U, the input to the controller, and the error, the tracking error. And of course here I don't forget to add the limitations for the actuators. So this is about loop shaping. The idea is that if I use a PI, a PID, and if I see that the phase margin, that the perturbations are rejected, but the phase margin is not enough, I may decide to add in parallel, or in series with a PI or PID transfer function, which is a transfer function which is augmenting to the value that I want the phase margin. And of course the other margins, right? Okay, so the last method which I want to show you is pole placement, or structure, RST structure. And for this, we need to remind ourselves again all the matrices, all the transfer function between all the inputs or the outputs. Why? Because here the method is a bit different. I'm going to place myself the poles into the closed loop system. So I'm going to impose myself the time response for the system. So just to tell you here, so if I have the pre-filter, yeah, I'm going to, so here I remind you what is a slow or fast response time, depending on the positions of the poles within the unity circle. And let me just show you what is RST structure. So the classical closed loop structure that we have here. So here I have R over S. Here I have A over B over A. This is the model. B of Z over A of Z. T over R. Okay? This is the notation that I did. So this here is the same thing with written. This is equivalent with writing. So this is the reference or consign with writing. PZ here. One over S of Z. This is why we call it R, S, and T structure, because what I want, I'm going to place the poles in this closed loop so that I can find the polynomial R, S, and T. I have to find the coefficients of these polynomials. So if you want to demonstrate that this is exactly this, well, it's clear. Let's say that the closed loop of this HBF, it is F of Z, right, multiplied by SC 1 over HC. Yes, you can replace and you can see that HBF, it is T over R of R of Z multiplied by H. Well, I have R Z or multiplied by BZ over 1 plus SZ AZ or 1. Yes, I wrote too many things. I'm getting tired. So H, it is B. C, it is R. And then 1 plus H, it is B. C, it is R over S. You do the calculations and you'll see that is the same thing with writing here. HZ here is T of Z multiplied by 1 over SZ multiplied B of Z over HZ. Here it's 1 plus 1 over HZ BZ AZ multiplied by RZ. Yeah. If you do the calculation of this and of this, you will see that they are equivalent. They are really equivalent, right? This will go with this, and you will obtain exactly what you want. Let me just write directly here, T of Z, BZ, AS plus BR. So this one is the same thing, because this will go with this, and then you have the same denominator, so it's the same thing. Okay, so these two structures here are equivalent. But this structure here helps us in the sense that if I'm going to have a more algebraical way of finding the parameters of our controller here, right? Again, I'm telling you, it's not a different controller. It's also a PID. It's just that I put it in a different structure. I wrote it as a fraction of two polynomials, and I put it in this structure. But again, it's the method, the controller itself, it's also a PID, okay? It's just that the structure of this PID is a bit different. I write it like this so that I can algebraically find the tuning, the parameters of this control. So what I'm going to write? I'm going to write HZ, it's B over A. I have the polynomials of the model. The controller C, it is R over S. So I need to find out this R and S, the coefficients of these polynomials here. This is what I want to find. And if I say that it's a corrector proper, it means that the denominator here has the degree bigger or equal than R. Yeah, strict man proper, or the system which is causal. It means that S is bigger than R. Okay, so this is the transfer function. The characteristic polynomial, as you can see, it's AS plus BR. And what I said, this is a characteristic polynomial. Sometimes we call it equation Diophantine or equation de Bézout, or polynomial of regulation polynomial. So this polynomial here, for this one, we need to choose the poles. Yeah, it's up to us to impose them, to choose them. Such that, of course, we respect all the constraints that I showed you before. So how we choose the degree of the polynomial P? Well, the degree of the polynomial P is the maximum between degree de A plus degree de B or degree de S plus degree de R. Okay, so I think I said differently. So degree of the characteristic polynomial is the maximum between, sorry, what I'm saying. So it's the maximum between degree of A plus degree of S, degree of B plus degree of R. Because, of course, that I would like to take the degree of the polynomial is the degree of the transfer function in closed loop, of course. Okay, so this polynomial, either I can take it with different poles, which is a bit more difficult to choose it with different poles, or I can take poles with the same multiplicity, in the sense that if the degree is P, I will have one pole which appears P times, so with multiplicity P, yes? So I'm going to choose this pole, Z0 here, by imposing the time response that I want. For example, here is the exponential minus 80e over time response at 95%. So if the degree is 1, we have a table where which tells us the value of this A is 3. If the degree of P is 2, the value is this, and so on. This is taken from somewhere. It's not me who invented this, but you need to, let's say, trust me over this. So this was the degree of the polynomial, the characteristic polynomial. But then how I choose the polynomial S and R, the ones for the controller? Well, S, I'm going to choose it such that it contains an integrator, to have static error void or null. So S should have a pole in Z equal 1. And the degree of R is the maximum between degree of A and degree of B. Of course, it's normal, right? Because if I want the controller which has at least the degree of the transfer function of the model, it should be that R here, the degree of R is the maximum between degree of A and degree of B, right? Okay, and degree of S, to have a controller which has which is strictement proper or causal, S should be bigger or equal than R, or proper, not necessarily strictement. It's strictly bigger. And then I'm going to put all these equations in a matrix form if it's necessary, because what I want is to find out the coefficient of S and R here. Because the coefficients of A and B, I know them. And this is me who places Z0, Z0. Here it's me who places it, right? It's me who said that I want this pole, which gives me this time response, yeah? And then it's just some... then it's just some equations to solve, some equalities to solve, of course, depending on the degree of our polynomials, R and S. So once we have that, we can also check if we need to add a pre-filter, right? To have static error null. So what does it mean? It means that the transfer function between the output and the reference should be 1, so that the output goes to the reference, right? Yeah. And then for the pre-filter, first we start with something constant, and then we add some other choices. And as an example, let's take the example where I have a very complicated system, an ugly one, third order degree. Yeah, you can do this, and it's the limit of stability because P here it's 0, right? So it's in Z is Z minus 1. So, okay, so I write my model in discrete time. So this model is a fraction of two polynomials, A and B, B over A. I choose the degree of R. The degree of R is the degree maximum between the degree of A and degree of B. So maximum of A is 2, maximum of B is 3. So I have this, the fact that R is 3, the degree of the polynomial of the controller. And then to have a controller strictement proper, I'm going to choose S4, strictement bigger than R. And then for the closed loop system, it's 7 because it's maximum between degree of A plus S, 2 plus 4, it is 6, degree between B, 3, and R, 4. Here I have 7. So this is 7. The time response, I would like to have 1 second. is me who imposes this. So it means that the A here, if I want 1 second here, the A, you go to that table. I did not even add for degrees more bigger than 4 because here I took it 7, but still it's not necessary to know by heart these values. Okay. So this is the pole that I choose, 0.8, which is imposed by the what time of response I want. And then I do the analysis. And the analysis tells me that the module margin is not sufficient, that the phase margin is not sufficient. So the controller I synthesized is not enough. Yeah, it's not enough. So what I can do? Well, it's not enough because actually I should take more precaution over this integrative part here. This here in the parentheses, I have actually faster poles. So this was do not change too much the response time of the system. So what I'm going to do, I'm going to approximate this model. I'm going to do a hard approximation with an integrator, 3/p, because I need to be more careful to this integrator. So if I take it 3/p, then it will be easy. I have found the model in discrete time, and I'm going to choose the degrees, degree of R, degree of S, degree of P. I'm going to impose the time response. 1 second. Depending on the degree of P, in my case it's 3 here, the A there, it is 6.3. And I'm going to do the analysis, and you can see that now I augmented a bit the module margin, the phase margin, and I start to have satisfactory results. So here is the response, ion step, right? Don't have. I obtained tracking error 0, a bit slow, but it's fine. And here is the rejection of perturbations. Yeah, so that was it for the method pole placement. We are going to do some exercises, and I hope that you will understand better. So the next hour, we are going to do some exercises. So let's take a break before the exercises. Let's take a 10 minutes break. And then we do some exercises for PID tuning. So now it's 8:58 for me. So we meet at 9:12. So I came back. Let's do some exercises. Let's hope that the exercises will be insightful enough so that you can grasp all this information. So let's do exercise 16, and let's start yeah, I hope you can hear me. Yes, I turn on my microphone. It's good. So let's see, exercise 16. So we have this transfer function. It's a continuous time transfer function, and I'm going to ask you to implement a PI controller in continuous time, such that we respect these margins and this constraint here, in the sense that amplification debris and haute fréquence limit is limited at 10. So it means that the gain of the controller in high frequency is limited at 10. So I want to synthesize a PI. I would like to then find out the sampling time for implementing this controller for this function, for this transfer function. And then I'm going to ask you to discretize using the testing method. And hopefully, if we have time, we solve this exercise to synthesize an RST structure for a PID controller. If we don't have time, maybe we can meet next time and we can have this exercise finished. Okay, so let's see. This is the exercise 16. So I would like to have gain margin bigger than 0.5, phase margin bigger than 45 degrees, and the gain of the controller when omega goes to infinity, I remind you that we are in continuous time, should be smaller than 10, yes? Then discretization, we need to find out the sampling time and then to discretize the controller using testing method. Okay, so first of all, let's see this model. Is it stable or not? HP is stable or not? What do you say? Is it stable or not? Are you still there?
Yes.
Great, great.
It's stable.
So yes, it's stable, right? We are in continuous time, but the real part, yes. Yes, the system is stable. Is stable since the pole is -1/50, so real part negative, yeah. So this is why we will decide to use the pole compensation method to synthesize our controller. Okay, so I'm going to choose a PI, yes, because I have an order one, yes, model. So of course that I'm not going to choose higher than this, at least equal to this, a PI controller in continuous time, Cp equal K1 plus 1 over Ti. Yes, so this is the form of a PI controller. So what I want is to find out K and to find out Ti, and then of course to analyze all the margins to see if the constraints are satisfied. Okay, nice. So I remind you that we write this like a fraction, yes, Rp over Sp. And then I'm going to write my model HP V over AP, right? So for the controller CP, it is K1 plus TIP over TIP, and it's K TI P plus 1 over TI over TIP. Yeah. So I'm going to choose the zero of this polynomial, the solution of the polynomial equals with the one of the HP. Yes, or AP, the model here. Yes, the model HP. It is 2 over 50p, so 0.04 over p plus 1 over 50. Yeah, so these two here to compensate for the dominant pole. We choose Ti equal 50, right? Or P plus 1 over Ti equal P plus 1 over 50. This means Ti is 50. So I find out the integrator. Nice. How do I find now, if I find out the integrator, this is Ti, how do I find K? Can someone tell me which condition I can use from here such that I can find K? Which condition from here I should use such that I can find K? I found out Ti, but to find K, what condition should I choose? What condition from the hypothesis should I choose? Great. One of them is this one, exactly, that the gain of the controller at high frequency, it is limited at 10, right? So let me see. C over G omega, right? It is, so if I go back here, it is K 1 plus T I G omega, 1 G omega P, right? So when omega goes to infinity, what I obtain? Well, I obtain that K smaller than 10. Nice. So I found out one limit for K. Is it over? What condition should I impose now? What is the next condition that I should impose now? Can you tell me? What I should do next? what is the condition that I should also respect? Hui, can you tell me? What is the condition that I should also satisfy, should verify? Can you tell me, Hui? So, Hui, can you tell me what condition I should check now? I'm waiting for your response. Even if it's not the perfect one, but I'm waiting for an opinion. Are you still there? Do you have an opinion? Okay. So you say that the stability margin. Well, of course that we have to also check the stability margins. But before checking the stability margins, of course that I first need to check the stability. And then if I'm far away from the stability or not, yes? So first of all, I need to check if the system is stable for these values. So first, stability. Stability and then margins and so on. For stability, I need to have HBF, right? HBF is the model multiplied by the controller AC. Great. So, what I'm going to have here. So I have 2K let me just remember because I don't remember. Two over 50p plus 1 multiplied by my controller. My controller is K 1 plus TIP over TIP. But I remind you that TI is exactly 50. So 1 plus exactly the same thing. With TI 50. So if TI is 50, this goes with this. This goes with this. And I'm going to obtain HBF of P, of course, because we are in continuous this time. It is 2K over TIP plus 2K is the same thing with writing 2K over 2K plus 50p. So stability implies that minus 2K over 50 should be less than 0, right? The real part negative, yes? I remind you that we are in continuous time. So this means that K bigger than 0, yeah? So I found out that TI is 50 and that K belongs to 0, 10.
Nice. And now, like what Hui was telling us, now we are going to check the stability margin and the rest, right? So let's check the gain margin. The gain margin, yes, should be bigger than 0.5. So the gain margin, it is 1 minus HBO of G omega, yes, when we have the argument of HBO of G omega equal minus P. Yes, HBO, first HBO of G omega. HBO of P, it is H of P multiplied by C of P. So it is 2K TIP, so 50P plus 1 over 50P plus TIP. This 2K over 50P. So HBO of G omega, it is 2K over G omega 50. Is minus 2K G over 50 omega. Yes, so the argument of this it is A tangent, imaginary part over real part, zero real part, imaginary is this. So it is A tangent over minus infinite, so it is minus P over 2. So what does it mean? Because I wanted this, so it means that the argument or the phase never arrives to minus P. So it means that since HBO never attains minus P, this means that the gain margin, it is actually, can someone respond me? What is the value of the gain margin? Again, Hui, what do you think? What is the value of the gain margin? Since HBO never attains minus P. What do you think? Or some other colleagues? Let's see. Let's see. Lenan. L-N-H-A-N. Lenan. Do you think that you can tell me what is the gain margin? Since this never attains minus P, the gain margin is so the gain margin is infinity. So it means that it's always bigger than 0.5, right? Not even equal. Okay, so I found out the gain margin. Then let's see the phase margin. The phase margin, we said that it's P
plus argument of HBO of G omega. When HBO of G omega is 1. Well, it's simple because I already computed the argument, and it's this minus P over 2. So the phase margin, it is P minus P over 2, so it's exactly 90 degrees. Very nice, right? So let's see. Let's see this exercise. Let's implement it in MATLAB. To check if we did correctly our computations here. So let's write our transfer function, yeah? So I write here our transfer function. So our transfer function is 2 over 50 p plus 1, yeah? So again, don't forget that here in France, and I wanted to keep as well, the Laplace transform, it's p for us, yeah? But yeah, it's the same thing. So here, as you can see, I describe my transfer function, my model. And then I said, okay, I found out that Ti is 50, yes? And I found also that K is between 0 and 10. Let's take it, for example, 2. I took it 2. Okay? I remind you that the form of the controller that I choose is this one. K 1 plus 1 over TIP. So in MATLAB, if you want, you have K plus K over TI 1 over P. This is the form that MATLAB gives us. Yeah. So if you want, you compute this K over Ti. Yeah. To use the PID form from MATLAB. So K it's KP, may I call it KP over TI. Yeah. And then for the derivative part, I don't have anything, it's 0, right? So what I do? Let's define our controller. Yes, the one that I found out here, yes? So I'm going to define it with PID because I have found the coefficients, the tuning parameters here. So let's define it. PID over KP, KI, and KD. So this is my controller, right? This is the controller that I found, that I find. Let's now do the analysis. I can check, of course, if the gain in high frequency is smaller than 10. I can check the stability. I can check the stability of the closed loop system. Let's look at the closed loop system. So I'm going to do feedback of the closed loop system of HC. F is 1 because I don't have anything. Yes, I don't have anything on the, F is 1. So I have here the controller, here I have the model H, and here I don't have anything. So this is why I take it 1. Yeah. It's clear, right? If I want to use feedback in MATLAB, I need also to give the value of the transfer function, which is on the closed loop system. So in my case, it's 0. It's 1. Okay. So this is the transfer function in closed loop. This one. Let's find out if this is stable. Right? We do roots for T1, the num of 1. So I'm going to check up. Let me see what I get wrong. This is T1 then. So this is my denominator, and I have to do roots of this, right? Yeah. So is the system stable? Yes, so I did roots of T point then of 1. So the denominator. Maybe I did not put a parenthesis. So these are the poles. So you can see that both they have the real part negative. So the system is stable. Great. So the system is stable. And we can see this also when plotting the step response. So you see, this is the step response. So I go to 1. And of course that the system is very slow, it's 60 seconds, due to the dynamical model that I choose. I remind you that H, the dynamical model, is 2/50s plus 1. So due to this, the system is quite slow, okay? Next, I did not finish, right? I cannot show just the response time and that's it. I should also check. So I check the stability, I check the response time, but I also want to check if I'm far away from stability, margins of the stability. So I need to check the stability margins to see if I have what I obtained here, to see if I have gain margin infinity and the phase margin 90. Okay, let's do this. So, of course that I do this for the open loop system. Yes, HBO, right? And I'm going to compute the margin, the gain and phase margin. So margin of HBO. So what do we see here? Well, we see exactly what we computed. The gain margin, it's infinity, right? Because the phase margin, it's always a minus P over 2, never attains minus P, yes? And here it is the phase margin, which is 19 degrees. Of course, I look at 0 decibel and I see that the phase margin is 90 degrees. Okay, nice, beautiful. What else it remains? Here it was the step response, yes? This is the step response. I told you that it's quite slow, 60, 70 seconds at the time response, okay? Then let's look at of the controller. Let's look at the controller, because if you remember, we said that in high frequency, the controller should have less than 10, right? The gain. So this is why I'm going to plot the diagram, the body diagram for the controller. What do you see here? Let me do grid on. So what do we see? You see exactly what we wanted. In high frequency, the gain of the controller is less than 10 decibel. Less than 10 decibel. Less than 10 decibel, yes. Beautifully, right? What else it remains? What analysis should be done? Rest. What else it remains? What plots you want to see? What it remains? Well, it's written here. I wanted to also see the module margin, right? How robust is the system, right? So let's see. I compute the sensitivity function, which is 1 over 1 plus HBO. Yes, this is the sensitivity function. And the module margin is the inverse of norm of the sensitivity function. So the module margin, it's 1, right? It was expected, to be 1 because the gain margin is infinity and the phase margin is P over 2. So of course that the smallest distance from, so if you want, you can do Nyquist of HBO. I don't know why it doesn't work. It's correct, right? Yes. And so Nyquist. Well, this is weird. I'm going to do just body mag of the sensitivity function. And like this, we can see, this is the sense, okay. It put it on the other figure. So you can see this is the sensitivity function. So the maximum is 0 decibel. So the maximum of the sensitivity function, it is at 0 decibel. So it means that here 0 decibel, I have 1 over the module margin, which is actually 1. With 0 decibel, it's 1. So it's clear that the module margin is 1. Nice, right? Okay. So we have checked this exercise that we did correctly. It remains to find out the sampling time, yes, for this system, yeah. Just to see here how to find out the sampling time. Well, the sampling time, what I'm going to do? Well, I'm going to place myself at 0 decibel, because this is simple for me, 0 decibel, and I will impose that this should be less or equal than omega max, which is P over TE, right? This is the condition that I would like to impose, yes? Of course that you can choose any other pulsation here, which all the others should be less than omega max. But for me, it's simple to compute the one at 0 decibel because I have this nice formula, right? This is at 0 decibel, right? So HBO of G omega is this one, 2kJ over 50. I'm going to call it 0. 1, since it's in module, I'm going to have omega 0, it is 2k over 50. So this omega 0 should be less or equal than omega max, which is P over TE. So this is equivalent with saying that 0 smaller than TE, so of course the sampling time should be bigger than 0, smaller than, so 2k over 50 should be P over TE. So here I have 50p over 20k. Of course, with k, you take it between 0 and 10. Nice, right? And then the other one is to use Tustin to discretize your controller. This means that in C of P there, where you find out that K is 1 plus 1 over TI P, P is a denominator, of course. You should replace P with 2 over TE, Z minus 1 over Z plus 1. And then you discretize your controller using Tustin. Then, one question. If I should actually, here I choose to synthesize a controller in continuous time. But if I want to synthesize the controller in discrete time, what should I do? Well, first of all, I will have to discretize HP to have the discretized model, right? And I can discretize it either with a zero order hold, either with Euler, whatever. Then I will choose a controller. So for discrete time, I will choose a controller CZ, right? Which is K, 1 plus Ki over 1 or Z minus 1. Yeah. This is the form that I want to take for the PI. Yeah, so we have to find out K and Ki. And to find out K and Ki, I will follow the same steps here. I will have to compensate for the poles, just that I will be in discrete time. Then I will have to impose this condition here, that in high frequency, the gain should be omega, goes to omega max now, should be less or equal than 10, or less strictly than 10. So when I do this, it means that Z goes to minus 1. Yes? So this is the only thing that changes. And then for the stability, we need to check the stability property. Here, real part negative. Here, for the stability, I will have the poles of HBF, boucle fermée, closed loop, should be in the unity circle. And then the same, the gain margin and everything should be computed the same. It's just that here, I'm not going to have HBO of G omega. I'm going to have HBO of exponential in discrete time. I'll have HBO of exponential dg omega. And that's it. So these are the only differences, but the steps are the same. The same. Everything the same. Okay, so I'm not going to have the time to finish the other exercise, but this doesn't mean that you cannot continue it. And if you want to ask me questions, you can ask me by mail as well. And of course, I hope to meet you on 11th of December. I'm going to be in, let me see. So on 11th of December, I'm going to be in Ho Chi Minh, and I hope I can do more exercises with you, and also in MATLAB. So please check the folder that I'm sharing with you, because there you will have also exercises in MATLAB, and also some to finish these exercises in the PDF that I provided you. Okay. So it's fine. You have questions? Yeah, I see that. You have questions? So maybe not. Okay. Okay, so I hope to see you. Thank you for your presence, and yeah, good luck. Good luck with the other courses.
Okay, Professor, thank you. And
Thank you.
we will see you in December.
Okay,
in
great.
Vietnam.
Great.
Okay.
Great.
So,
See
okay.
you.
See you. Okay, bye
Thank
bye.
you. Bye.
Yes. Mm.